Hello and welcome back to Nunley Math. I'm your host, Aaron Nunley. I appreciate you joining us so much here today as we continue our discussion of exponents, exponential functions, exponential growth and decay, interest, compound interest, and a lot of things involving banking and exponential growth. We've got a lot to cover today, so let me go ahead and get started. Just in the way of review, you'll remember in our last video in the series, we talked about the exponential growth function and how the exponential growth function says that we start with a certain amount and we have 100% of that amount plus some rate of growth over a period of time, and that gives us our new amount. So for example, we would look at something like this. Suppose a conservation scientist discovered that there were approximately 800 deer living in Butler County. She predicts that the population growth is averaging about 11% per year. How many deer would she expect to see living in Butler County 7 years from now? When we go to set this up, it's going to look something like this. There are currently 800 deer. Next year, we expect to have 100% of those, or all of those back, and 11% more. Or in other words, we expect next year to have 111% of our current population. And then the year after that, we expect to have 111% of that new amount and 111% of that new amount, so on and so forth for 7 years. Since we're going to be multiplying by 111%, or 1.11, repeatedly, we would make that to the 7th power. Now, if that's unclear to you, I'd recommend going back and watching the previous video where we explained why this is an example of exponential growth instead of linear growth. For today, that really is sufficient to get us started. This amount you can type into your calculator. Notice it does fit the exponential function y equals ab to the x pattern. Notice as well that if we were to graph it, we would expect it to grow slowly at first and then faster and faster over time. But we end up with 1660.928, or approximately 1,661 deer. The first year after we grow, we would expect to have 800 of them back, that's 100%, and roughly, what, 11%, 88 more, something like that. We would expect to have 888. So the first year it's going to grow just by a small amount, 88. The next year we would expect it to grow by slightly more, slightly more, slightly more, and so on and so forth. Here's another example. This one is exponential decay, which is very closely related to exponential growth. In exponential growth, we had a starting amount, and we were growing by a certain percent. So we took our starting amount, 100%, and grew or added 11%. In this second example, instead of looking at deer population, we're looking at wolf population. Notice what this says. Part of the increase in the deer population can be attributed to the decline in the population of predators, specifically wolves. Suppose there were 250 wolves living in Butler County 10 years ago, but the population has been, here's the key, declining by 5% each year. How many would you expect to live there now? Notice in an exponential growth equation, we start off with 100% of our population, and we were growing, in this case, by 11%. But in an exponential decay function, instead of growing by a certain percentage, we're going to be declining or decreasing by a certain percentage. In the case of this problem, we're declining 5%. It's going to look something like this. I had 250 wolves. That was all of them. That was 100%. But I lose or decline 5% every year. Since it's going to be every year, I'm going to be multiplying by 0.95 or 95% over and over and over every year for 10 years. Now notice 95% is our growth factor or our decrease factor? It comes because we are declining 5%. 100% minus 5% says what's left is 95%. If we have that decline year after year for 10 years, notice, by the way, it does meet the exponential function pattern, we're going to end up with 149.68, or roughly 150 wolves remaining. 150 wolves remaining. Here again, the point here is to illustrate the difference between an exponential growth and an exponential decay. I do have one more for you. This one we're going to use as a catalyst for the rest of our discussion today about compound interest. It says, when you put a $500 charge on your credit card, the bank charges you 20% interest every year. If you never charge any other items and you never pay it back, what would your debt be in 5 years? What would your debt be in 5 years? Notice, just like the exponential growth problem on the previous slide, we started with a certain amount, 500. We are going to owe 100% of that amount, but the amount we owe is going to increase 20% every year, so that what I end up owing at the end of 1 year is 120% of what I started with. Here again, that does meet the y equals ab to the x pattern. And since that's going to grow every year, I have to do it 5 times for 5 years. That, of course, we can type into a calculator, and we end up owing $1,214.16. I do, in this example, want to go back and discuss really quickly one more time what happened here, because this is going to lead us to our next discussion. The bank says, oh, you have a loan of $500. So at the beginning of the loan, they've given you the $500. You owe them 100% of that back. So at the very beginning, you're going to owe them $500. But after a year, they're saying, well, you need to pay back the $500, 100% of that, and 20% more, or 120% of what you originally borrowed. So instead of owing them $500, you now owe them $600. Well, at the beginning of the next year, you owe them $600. That's what this is $600. I see that from the previous line. And I'm going to owe them 120% of $600. You see, my base or starting amount at year 0 was $500, but I don't owe $500 anymore. I owe $600 at the beginning of the second year. So during that second year, they're going to charge me $600 times 120%, or $500 times the 120% twice, for a total of $720. We discussed in the last video that 20% of 500 is smaller than, or is about $100. That's actually smaller than 20% of 600. 20% of 500 was $100 in growth. We're going to owe them $100 extra. The next time it grows, we owe them 120. It's growing faster. Remember, exponential functions start off growing slow, and then they grow faster and faster. At the beginning of year 3, I owe them $720, or 500 times 1.2 times 1.2. Again, that's from the previous line. That's the $720. But they're going to charge me 120% of that. The 100% I already owe and 20% more, making it 500 times 1.20 to the third power, or $864. Notice, what I owe them increased again. The first time I owed them $100 extra. The second time I owed them $120 extra. This time I owe them an extra 100, is that 44? An extra $144. My rate of growth keeps increasing every time we compound, or every time we start a new year, because that first or base amount is getting larger. Does that make sense? Hopefully it does, because it's real important we understand that, because I've kind of bent the truth just slightly in my explanation of this. in that this is not really what banks do. This is the foundational mathematics behind what banks do, but banks actually do something slightly different from this. You see, the bank does not simply charge you 20% every year. Banks realize that 20% of the 600 is $120. 20% of the 600 is more than 20% of the 500. 20% of 500 was only $100. And they realized that 20% of the 720 was 144, which is more than 20% of the 600. And they realized that if we were to calculate 20% of 864 to get the next year, that's going to be bigger. They realized that the money they're earning grows faster every time this number right here gets bigger. So it's to their advantage to take that base amount and grow it as quickly as they can. This process of changing that base number, changing the starting amount of our calculation, it's called compounding. In other words, instead of waiting till the end of the year like we've been doing to recalculate, they can make extra money by recalculating more often. There's a formula for that. This formula isn't going to make a whole lot of sense at first, but I am going to go ahead and explain it, and then we'll come back and talk about this formula a second time. I've recopied the last problem onto this slide. You notice it's the exact same thing from the previous slide. I just shrunk it down a little bit. I even recopied the table for you so that you could see that. Wow, that's a really bad bracket. But let's look at this. Suppose the bank decides that instead of compounding every year, they're going to compound twice per year. They're going to compound twice per year. And I want us to compare what those tables look like. You see, just like before, they're going to charge us $500 because that's what we borrowed. So at the beginning of the problem, we owe them $500. And they're going to charge us 20% per year. But instead of waiting till the end of the year, we're only going to go out half a year. Well, since we've gone out half a year, they can't really charge us 20%, so they charge us half of that. In other words, in half a year, they'll charge us 10%, and then the second half of the year, they'll charge us the other 10%. So instead of charging us 1.20 like they did in the first problem, they're only going to charge us or multiply this by 1.1, which is $550. Now, if you look over here at year one, you'll notice that it was $600. It makes sense if it's $100 for the whole year that it would be $50 for half a year. So they've not done anything unfair at that point. But here's where this gets interesting. The second half of the year, they're not going to charge that second half as 10% of 500. No, no, no. Just like before at the end of the year, they went from charging us a percent of 500 to charging us a percent of 600. Now, in the middle of the year, they're going to recalculate. This is no longer a 500. This is now a 550. And then they're going to charge us 10% for the rest of the year. In other words, instead of charging us 20%, they've charged us 10% for the first half and 10% for the second half, so they've charged us that 10% twice. But notice what happens. This is now $605. Over here, one whole year only raised it to $600. But by doing this twice as often and charging us half as much each time, they've allowed themselves to gain an extra $5. Because over here, the 20% was 10% of 500 and 10% of 500. But in our new problem, the first 10% was 10% of 500, the second 10% was 10% of the 550. Does that make sense? You might need to go back and listen to that again. That's a little bit tricky, a little bit complicated, but it should make sense after you think about it a couple times. Now, at the end of 1 year, I now owe them $605. So we're going to start the next half year. Remember, this is just from the line above it. This means $605. That's this right here. I'm going to take this $605 and multiply it by 10% for the first half of the next year. So I've multiplied it by 1.10 3 times now, making it $665.50. Just like during the first year, halfway through the year, I'm going to change that base number. The base is no longer 605. Now it's the $665.50, which is represented by this. Notice this is the exact same thing as the previous line altogether. This entire amount, this $665.50, also gets multiplied by 1.1, which is 110%. We've done that 4 times, giving us $732.05. Compare 2 years using this method to 2 years using the previous method. If we compound once at the end of each year, we would owe $720. Now that we're doing it twice a year, we're up to $732. We've managed to eke out a little bit of extra money. Here's what that's going to look like written as an equation. Instead of having 500 times 100% plus 20%, and doing that 120% 5 times, instead of changing it 5 times, I'm going to do half the 20%, which is only 10%. But instead of doing it 5 times, I'm going to do it twice as often. In other words, when I go through this, I'm going to charge 10% interest every half year for 10 half years. We would end up owing $1296.87. Compare this to what we owed before. They've managed to eke out an extra $82.5-ish. See how that works? Now, we can compound as often as we want, which is why when you go to get a loan or to sign up for a credit card, it's very important you read carefully, because if they just compound at the end of the year, it's very different than if they compound twice a year or semi-annually. But they don't even have to compound semi-annually. Notice I've copied my annual compounding here for the 3rd time. This is the problem we just solved where we compound twice a year. But I don't have to compound twice a year. I could compound quarterly. Quarterly means divide the year into fourths, or compound 4 times a year, which means instead of charging me 20% like we originally did, we're going to take that 20% and we're going to divide it into 4 equal sections. And then, because we are dividing it into 4 equal sections, or groups of 3 months, or 1/4 of a year, when we go to calculate it, we're not going to do it 5 times. We're going to do it 4 times a year for 5 years. Or we're going to calculate this amount, this 5%, 4 times a year for 5 years, or 20 times. Remember, doing it once a year for 5 times is the same amount of time as doing it 4 times a year for 5 years. And from here, it's just simple calculation. Notice, if we compound at the end of a year, we owe $1214. If we do it twice a year, we owe $1296. If we do it 4 times a year, we're up to $1326. That's because we're changing this first number more frequently. Now, here's what the formula says. Just like before, we had an equation for all exponential functions that said y equals some starting amount times some factor over and over. We then went through and said, if we're talking about compound interest, we take the principal, which is what we started with, that's the same as A, that's your starting amount, and it's always 100% either plus if it's growth or minus if it's not growth, some kind of a rate. So it grows 10%, it grows 5%, it shrinks 10%, we don't know. But we're going to do it over and over. This formula is just an example of, or a specific iteration of, this formula. It's just a little more complicated. We're doing the same thing here. We're taking this formula and we're inserting it over here. We're just adapting it a little bit. It's still some starting amount. We still have to pay back 100% of that amount, plus they're going to give us an annual interest rate. They'll say 5% per year, 10% per year, 50, whatever. And then instead of waiting till the end of the year to do our computations, we're going to do our computations 2, 3, 4, 5. We're going to do the computations repeatedly throughout the year. So we'll take whatever they're charging us, split it into even groups, and then we'll do that more often. Does that make sense? Let's try this again. You deposit $100 in a savings account that earns 6% annual interest compounded quarterly. I'm going to circle a couple things here. I'm putting $100 in, I'm earning 6%, and I'm compounding quarterly. Quarterly, you remember, means 4 times a year, and I want a function that's going to work for T years. So if I were doing this once a year, I would be putting in $100. I would owe 100% of that plus 6% more, and then I would do that every year. That's compounding annually. But this one is asking us to do our compounding 4 times a year. That means at the end of 3 months, we're going to recompute the base amount that's owed. And at the end of another 3 months, we'll do it. Then at the end of another 3 months, we'll do it. And we'll continue doing that all the way through. So I'm going to take that 6%. And since I'm doing it 4 times a year, I'm going to have to split that 6% into 4 equal size sections. But since I'm dividing the year up into 4 equal size sections, I'm going to be compounding 4 times as often. What that means is that when I do this, I'm going to be taking that 0.06 divided by 4, and since I'm doing this for 8 years, I'm going to be compounding 32 times. In other words, instead of doing 6% 8 times, I'm doing 1/4 of 6% 4 times as often. So instead of recalculating 8 times, I'm recalculating 32 times. There's our equation, and we can perform some computation, and we end up owing $161, or actually we end up saving $161.03. That's the $100 we started with plus $61.03 extra. Let's try one more. You deposit $300 into a savings account that earns 3% interest compounded. I'm going to circle this monthly. There are how many months in a year? 12. So in our original problems, at the end of every year, we would recompute what it was that we either owed or had saved. In this particular problem, we're not going to do it at the end of every year. We're going to do it at the end of every month. And then we're going to write a function for that, and then we're going to find the value for 20 years. So let's walk through this. If we were doing this every year, we put $300 in savings, we'd get 100% of that back, plus 3% interest, and that would happen every single year. But in this problem, we're going to take that 3% and we're going to divide it evenly among every month so that each month we earn a fraction of that 3%. And since I'm doing it every month, my final answer will have been computed 12 times more often. That's compounding 12 times a year. Notice we are doing 20 years here, so instead of doing it at the end of each year 20 times, we're doing it at the end of each month 240 times. 3% divided by 12 is 0.0025 or 0.25% every month, and from there it's just a little bit of computation. we would end up having $546.23 in our savings account. Hopefully this has been helpful to you. This has been worthwhile to you. Compounding more than once a year can sometimes be a little bit confusing for people, but the computation really is not that hard. Just remember, take your percent, divide your percent by how many times you're doing it a year, and then just make sure that you remember to multiply on the outside so you do it that many more times as often. As always, we do appreciate you taking the time to watch. We wish you all the best. Make sure you hit that like button. Make sure you leave us a comment in the comments section. Turn on your notifications. Be sure you subscribe so you don't miss out on any of the things we have coming for you in the upcoming days here on Nunley Math. Best wishes to you all. Take care.